In the previous class, we discussed Gauss law and the important points regarding Gauss law. So, those points we will now make use while calculating the electric field strength due to certain types of charge distributions. So, before going to the actual application of Gauss's law, let me discuss one important point. Consider a uniform electric field like this, in which I want to find out electric flux through a cylindrical surface. So this is the cylindrical surface. Now it is a closed surface I am choosing. So let this area be say some ds1, and this is the area say some ds2, and this is the side area. Now if I want to calculate the total flux through this cylindrical surface, so I am dividing the total flux into three parts. Flux through ds1, let me call it as say phi1, and flux through the surface ds2, let me call it as phi2, and the sideways surface, through that the flux be phi3. Now through ds1, what is the flux? So here phi1 is given by, so electric field strength E bar dot Ts1 bar, let us say. But you know the area vector, there is normal drawn, outward drawn normal to this area is in this direction, this is in this direction, whereas electric vector is in this direction. So the angle between the two vectors is 180 degrees, hence you will be getting EdS, because this area I am taking as ds. And similarly in this case, the area vector and the electric field vector are in the same direction. Therefore, in this case, this E bar dot ds2 bar can be written as, of course, sorry, here it is minus, okay, here it is plus EdS. So these two vectors are opposite. What you get is E minus ds. For this you will get E into ds, positive. And we assume these two areas are equal. So that's why I write as ds1 ds, ds2 again the ds, equal area. Due to the sideways area, the flux will not be there because the electric vector is perpendicular to the area vector. So hence these two are perpendicular. The dot product becomes 0. Therefore, E bar dot that ds bar, which is perpendicular to this electric vector, so that product will become 0. Therefore, if I calculate total flux, so that is phi1 plus phi2 plus phi3. Here, this is minus EdS plus EdS plus 0. So that will be 0. That means the total flux through such a cylindrical surface in an electric field is 0. So we have considered a uniform electric field. Whatever flux entering the surface is leaving the surface. Therefore, the total flux is becoming 0. In another way, if you apply Gauss law, which gives the formula like this for the flux, here total charge inside the Gaussian surface is 0. So therefore, the total flux is 0. Like that also you can explain. So this is one application of the concept of electric flux to show that the total flux is 0 because the incoming and outgoing fluxes are equal. Hence, total flux is 0. Or according to Gauss law also, you can say since there is no charge enclosed in the Gaussian surface, flux is 0. Okay. Now let us discuss the Gauss law's application. That is applications of Gauss. Under this topic, we will take three cases. One is electric field strength due to infinite line of charge. So let us see what formula we are going to get for the electric field strength at a point at a distance from r from infinite line of charge by applying the Gauss's law. So let us consider a wire of infinite length having uniform charge distribution such that lambda be the linear charge density. Now at a point at a distance r from this, I wanted to find out the electric field strength. For that, what I have to do? I imagine a Gaussian surface such that this point lies on the Gaussian surface. For the symmetry sake, I consider a cylindrical Gaussian surface like this. Such that this point lies on the surface, and say these two are the lengths. Say this is S1 and S2, and I will be taking a length of L. Elemental, let me say some L. Therefore, the charge on the elemental length of this wire is nothing but L lambda, length into the linear charge density. Therefore, from Gauss law, the flux due to this elemental length of the infinite sheet of charge, the infinite line of charge is given by that is L lambda by epsilon naught. So total charge within the Gaussian surface divided by epsilon naught. And from the relation between electric field strength and the electric flux, I can use this formula. Phi is equal to E bar dot ds bar. This is nothing but flux is a scalar quantity, and EDS cos theta you will get it. So due to the surface area, since the surface area is in the same direction of electric field strength, so this is the electric field direction, and the area vector of any element chosen on the surface will be the same direction, and hence you can write it like this: E into ds, or that is the surface area of the cylindrical area chosen, E into 2 pi r L. Okay, but what about the flux to S1 and S2? See, the area vectors for these two leads is along the length, so perpendicular to the field direction. So the area vectors for these two leads are perpendicular to field direction. Hence, there will be no flux at all, or dot product becomes 0. Hence, you can say there will be no flux. So the flux will be only through the side surface only. Hence, equating these two, that is E into 2 pi r is equal to L lambda by epsilon naught. This L gets cancelled, and what means E is equal to 1 by epsilon naught into lambda by 2 pi r. So that is the formula. Now here you can see that field is inversely proportional to the distance of the point from the linear charge, that is from the line of charge. The electric field depends inversely on the distance, so it is not depending on the square of the distance, that you must observe. Okay, that is how we can apply Gauss law to calculate the electric field strength due to infinite line of charge. If it is finite, what happens means you have to take the fringe effects also. The electric field will not be uniform for the same distance from the line of charge. Okay, so let us go to the next example, that is infinite sheet of charge. So let us take another example, that is infinite sheet of charge. Okay, so let this be the surface, some sort of surface where the charge density is uniform, and you know the charge density for the surface is represented with symbol sigma. So that is the surface charge density, right? Sigma be the surface charge density. And I want to find out at this point P what is the electric field, say at some distance r from the infinite sheet of charge. So I consider a Gaussian surface like this, and inside and outside. So on both sides I have to consider it will be in form of something like a pillbox. Okay. Now let us say this is S1, this is S2, and both are having same surface areas. So I will take SS only. The electric field here will be in this direction, radially outwards. Here also radially outwards, and definitely there will be no sidewise flux, because the field direction and the area vector are perpendicular. There will be no sidewise flux. So therefore, total flux is given by the 2 times the flux E bar dot S bar, like this. So here, why I am taking 2 means both we are having 2 surfaces on either side of the sheet of charge. Therefore, that will be the total flux. Since this area vector and field vector are in the same direction, I can take this product as E into S. So that is equal to 2ES. You may even consider it as say some ds also, doesn't matter. So let me take it as the element we are taking. So let us put some ds. So therefore I will write it as say ds. Then from the Gauss law, flux is given by total charge within the Gaussian surface by epsilon naught. So what is the Q here? That is sigma, surface charge density. And you know what is that area I am taking is say some ds. So sigma into ds, that gives the total charge by epsilon naught. Equating these two, that is 2E ds is equal to sigma ds by epsilon naught. So that the area term gets cancelled. Therefore, E is equal to, from this, sigma by 2 epsilon naught. So this is the formula for electric field strength at a point from the infinite sheet of charge. See, you observe that there is no distance term. So there that distance term is there. Here it is not there. That means the field with infinite sheet of charge is independent of distance of the point from the sheet. This is only in the case of infinite sheet of charge. So if you consider the point far away from the finite sheet of charge, then end effects comes into play. The formula is not applicable in that case. Okay. So this is the second example. So let us take a third one. So we consider a hollow sphere with uniform charge density. So let us take, let us suppose a sphere of say some radius r as uniform charge distribution on its surface. Let us suppose there is a charge q on the surface. Then for any point outside on the surface, the electric field strength is given by, according to Coulomb's inverse square law, q by r square. So at every point on the surface, that will be the formula, and the whole charge appears to be concentrated at its center. So as if the whole charge is at the center, the field strength at every point on the surface is given by this formula. But whereas if you consider a point inside, then what to do? So let us imagine a Gaussian surface such that the surface passes through this point, and let that distance be say some capital R. Now if you apply the Gauss law, that is flux is equal to total charge within the Gaussian surface by epsilon naught. But what is the total charge inside this Gaussian surface? 0 by epsilon naught. So that is equal to 0. So total flux through the Gaussian surface is 0. Now if you want to calculate electric field strength, that is E into surface area. So that is equal to flux E bar dot S bar. Therefore ES is equal to 5. But according to Gauss law, this is 0. Hence this is 0. Therefore electric field must be 0. That is, inside a cradle point on a hollow charged sphere, the field will be 0. So in that way, we can apply Gauss law for a uniform charge distribution on a hollow sphere, and you can show that inside a cradle point, the field is 0. So with this chapter is over. For this present academic year, this applications part is deleted. The remaining part of the chapter is there. Okay, right.